This is the 18th in a series of videos that I'm creating to support a course that I'm teaching in elementary number theory. And we just got done classifying all natural numbers that admit primitive roots mod that natural number. In other words, we discovered when there is a primitive root mod n. Now we want to move on to some other little topics related to primitive roots, including some applications. But before we do that, let's recall a couple of things. First of all, the order of a mod n is the smallest m such that a to the m is congruent to 1 mod n. We write m is equal to the order of n mod a with this notation. Next, the order of n mod a always divides phi of n. And then next, r is a primitive root mod n if the order of r mod n is equal to phi of n, so it achieves the biggest possible order. And then finally, we had that big classification theorem, which said there is a primitive root mod n if and only if n is equal to 1, 2, 4, p to the k, or 2 times p to the k, where p is an odd prime. So I didn't write down here that p must be an odd prime, but that's an important part of that theorem. Okay, so now we're going to prove the following proposition, which answers the question, if we've got a primitive root, how many primitive roots do we have? Is there some sort of formula for the number of primitive roots, or is it random? Well, it turns out that there's a nice formula. So we want to start by supposing that r is a primitive root mod n. So in that assumption, we're assuming that n comes from this list because we can find a primitive root in the first place. And then the result is that r to the m is also a primitive root if and only if the GCD of m with phi of n is equal to 1. Well, let's notice that that implies that if there is a primitive root, there are phi of n primitive roots. That's because we want to count up the numbers between 1 and phi of n that are relatively prime to phi of n, but that's exactly phi applied to phi of n. So let's start the proof with the reverse direction. So in other words, we'll assume that the GCD of m with phi of n is equal to 1 and r is a primitive root. And what we want to show is that r to the m is also a primitive root. Okay, so how can we do that? Anytime we see that the GCD is equal to 1, we probably want to invoke Bézout's identity. So notice that that means that there exist x and y, which are integers, such that m times x plus phi of n times y is equal to 1, like that. And then from here, we can write r to the first power as r to the mx times r to the phi of n times y. But then reducing that mod n using Euler's theorem, we see that this becomes congruent to 1. So that means we don't need to worry about the stuff in this green box. So that means this is congruent to r to the m to the x modulo n. But now that tells us that r to the first power, which again is just r, is a power of r to the m. So that means that any power of r, so notice that r to the a can be rewritten as r to the m to the x times a modulo n. In other words, we can achieve all residues mod n as a power of r to the m. In other words, since all residues mod n can be achieved by a power of r, that's part of being a primitive root, then all residues mod n can be achieved as a power of r to the m. That's given by this congruence. Well, that's exactly what it takes for r to the m to be a primitive root. That's like kind of the other definition of a primitive root, is that you achieve all of the residues mod n by going through the exponents of r. That's equivalent to this definition, which is over here. So just to reiterate, that means r to the m is a primitive root, where we use the fact that r is a primitive root to say that all important residues mod n can be rewritten as r to the a. And then we use the fact that we have a relative prime setup to produce this equation. Okay, so that finishes this reverse direction. So now let's prove the forward direction. Okay, we just finished the reverse direction. Now we're going to consider the forward direction. And we'll indeed do this by a contrapositive instead of a direct proof. So let's go ahead and suppose that the GCD of m and n, of m and phi of n, is equal to d, which is bigger than 1. So in other words, these are not coprime. Well, now notice that tells us that the LCM of m with phi of n is equal to m times phi of n over d. Okay, and then maybe we'll introduce some notation and call this equal to L. So that's a pretty standard categorization of the LCM as the product over the GCD. Now we want to see that here we run into a problem. So let's notice that we have r to the m to the power of phi of n over d is equal to r to the phi of n to the power of m over d by doing exponent rules, keeping in mind that d is a divisor of both of these, so these are natural numbers. But by Euler's theorem, r to the phi of n is congruent to 1 mod n, so we have this whole thing is congruent to 1 mod n. But what does that tell us? That tells us that the order mod n of r to the m is less than or equal to phi of n over d. Well, because we raised it to the power of phi of n over d and we achieved 1. Remember, the order is the smallest number so that when we raise it to that power, we get 1. So that doesn't mean that the order is equal to this. It means that the order is less than or equal to this, or really it divides this, but we'll just use this inequality here. But let's notice that since d is bigger than 1, this is strictly less than phi of n. So we have the order of r to the m is strictly less than phi of n. So that tells us that r to the m is not a primitive root. And that finishes the proof of this forward direction. Okay, so we've got one more little proposition like this, and then we're going to run through a couple of examples. Our next proposition is quite important for solving certain nice exponential congruences and polynomial congruences mod n. So let's look at the statement, and then we'll look at an important takeaway from the statement. So we want to start with a primitive root mod n. We'll call it r. Then r to the a is congruent to r to the b mod n if and only if a is congruent to b mod phi of n. So like I said, the important takeaway goes like this. If the base is mod n, then the exponent is mod phi of n. Okay, so let's prove this. This is actually not too bad. So let's do this forward direction. So we'll suppose that r of r to the a is congruent to r to the b mod n. But let's notice that that means that r to the a minus b is congruent to 1 mod n. But then we know that whenever we raise something to a power and get 1, that power must be divisible by the order of our base. So in other words, we have to have the order mod n of r dividing a minus b. Okay, but now notice that that means that phi of n divides a minus b. Because remember, r is a primitive root, so its order is phi of n. But that is exactly the condition to say that a is congruent to b modulo n, like that. Okay, nice. So now let's do the reverse direction. So let's go ahead and suppose that a is congruent to b mod phi of n. And notice that that means that a is equal to b plus k times phi of n for some integer k. That goes along with the definition of congruence mod phi of n. Now next, we'll see that r to the a is equal to r to the b plus k times phi of n, which is equal to r to the b times r to the phi of n all to the k power. But notice by Euler's theorem, phi of n is congruent to 1 mod n. So here we have r to the b times 1, or just r to the b mod n. And that finishes the proof of this proposition. Now let's go ahead and solve a couple of congruences using these strategies. Okay, for our first example, we'll solve x cubed is congruent to 5 mod 17 using primitive roots. Okay, so the first goal is to find a primitive root mod 17. So recall we had a test for finding primitive roots mod p in the last video, and that involved looking at the prime divisors of p minus 1. So let's notice that only 2 is a prime divisor of 17 minus 1 equals 16 because 16 is a power of 2. So for a proposed primitive root, we only need to check that r to the 16 over 2 is not congruent to 1 mod 17. Remember, the general rule is we need to check that r to the p minus 1 over q, where q runs through all prime divisors of p minus 1. But here we've got a nice special case here. Okay, so let's first start to see if 2 is a primitive root. So we need to check 2 to the 16 over 2, which is obviously equal to 2 to the 8. But we'll use the fact that we're working mod 17 to simplify as much as possible. So notice this is equal to 2 to the 4 times 2 to the 4, which is 16 times 16. But notice 16 mod 17 is negative 1. So this is congruent to negative 1 squared mod 17. But that's a problem because that's congruent to 1 mod 17. So that means that this is not a primitive root. 2 is not a primitive root because its order is 8. It is not 16. So now let's check 3. So we'll check 3 to the 16 over 2, which is equal to 3 to the 8. Let's see what we get for that. So again, we'll do a trick. This is 3 to the 3 times 3 to the 3 times 3 squared. But then notice that 3 to the 3 is equal to 27. So we have 27 times 27 times 9. Now we'll start reducing mod 17. 27 is congruent to 10. So here we have 10 times 10, which is 100, times 9, which is 900 mod 17. Now you just have to reduce 900 mod 17. I'll let you guys check. That is, in fact, equal to negative 1 mod 17. But negative 1 is not equal to 1, so that tells us that 3 is a primitive root. So that's the first step of any problem like this, or if you're going to solve a problem like this using primitive roots. So let's bring that fact to the top and then we'll continue on. Along our goal to solve x cubed is congruent to 3 mod 17, we have determined that 3 is a primitive root mod 17. So from here, we'll set x equal to 3 to the y. So notice if 3 is a primitive root, then any number that's relatively prime to 17 can be written as a power of 3 mod 17. So that includes this unknown x. So we're going to write this unknown x as a power of 3. This is all occurring mod 17. Now we can plug that into our congruence. So that gives us 3 to the y to the 3 is congruent to 5 mod 17. Now we need one more observation, and that is that 3 to some power must be 5 mod 17. And in fact, 3 to the 5 is congruent to 5 mod 17. So you'll have to work that out, but that's not too hard to check. Notice that's equal to 3 to the 3 times 3 to the 2, so you can do a little bit of reduction along the way, but there's a bunch of ways to check that. I'll let you guys check that however you want to. Okay, but now we can take this congruence and rewrite it as 3 to the 3y is congruent to 3 to the 5 mod 17. But now, like we pointed out in our last proposition, if the bases are occurring mod n, the exponents occur mod phi of n. So here, our bases are the same, so we can just extract the exponents and set them equal to each other mod 17 minus 1, which is phi of 17, or 16. So that means we have 3y is congruent to 5 mod 16. In some ways, we're taking a logarithm, and actually the next video will be about the generalization of a logarithm to this whole setup. All right, now we need to look for the inverse of 3 mod 16. But just by guess and check, we can see that that is 11. And that's because 33 is 1 more than 32, and 32 is a multiple of 16. So we can multiply both sides of this by 11. We'll get y is congruent to 55 mod 16. But then you can check that 55 is 7 more than 48. 48 is a multiple of 16, so this is congruent to 7 modulo 16. So there we have our solution for y. That tells us that x is equal to 3 to the y, or 3 to the 7. But let's notice that that is equal to 3 to the 3 times 3 to the 3 times 3 to the 1, because 3 plus 3 plus 1 is 7. Now we can notice that that's equal to 10 times 10 times 3 mod 17 for the same reason that we did on the last board. But that's going to be 300 mod 17, which reduces to 11 mod 17. So our solution is x is congruent to 11 mod 17. And then you can check that, in fact, this works. 11 cubed is congruent to 5 mod 17. So we have our solution. Okay, so let's do another example. So our next example involves an exponential equation. So we want to solve the exponential congruence 5 to the x is congruent to 17 mod 19. So the first thing that we'll want to do is find a primitive root mod 19. Now we would be in luck if 5 was a primitive root. And I'll let you guys check to see if 5 is a primitive root, but we'll just assume that it's not. And then start at the bottom looking for a primitive root on our own so that we can practice that strategy for finding a primitive root in the first place. Okay, so first of all, we need to look at the prime factors of phi of 19, which is 18. So of 18, but luckily there are only 2 and 3. Those are the only 2 prime factors. So we'll first check if 2 is a primitive root. So that means we need to calculate 2 things. We need to calculate 2 to the 18 over 2 and 2 to the 18 over 3 mod 19. Hopefully those are not congruent to 1 mod 19. If they are not 1 mod 19, then we do have a primitive root by our test from the previous video. Okay, great. So 2 to the 18 over 2 is clearly 2 to the 9, which is 2 to the 4 times 2 to the 4 times 2 to the 1, just by arithmetic. But 2 to the 4 is 16, so we have this is 16 times 2, 16 squared times 2, I should say, because here both of these are 16. But notice that 16 is negative 3 mod 19. That makes the calculation a little bit easier. So we have this is negative 3 squared times 2. But let's notice that negative 3 squared is positive 9 times 2 will give us 18. So this is congruent to 18 mod 19. But 18 is not congruent to 1 mod 19. So we're okay so far. This test worked out. Now we just have to do this test with the prime divisor of 3. That should be easier because 18 over 3 is a little bit smaller. Notice that gives us 2 to the 6. 2 to the 6 is equal to 2 to the 4 times 2 squared. Again, that's equal to 16 times 4 in this case. 16 is negative 3, so we have this is negative 3 times 4, which is equal to negative 12. I should say this is congruent to negative 12 mod 19, but negative 12 mod 19 is in fact equal to 7 mod 19. Well, that's not 1 mod 19, which means our test works for this as well, and thus 2 is a primitive root modulo 19, which means we're off to a good start. All right, great. So let's maybe take this information up and then we can finish this one off. Okay, so let's just reiterate where we were. We wanted to solve 5 to the x is congruent to 17 mod 19. We determined that 2 was a primitive root mod 19. Now we're going to do a little bit of a labor-intensive task, but it actually makes the whole program a little bit easier to work with, and that is find all powers of 2 mod 19. So notice I've worked from n equals 1 to 17. We know that 2 to the 0 is 1. Furthermore, 2 to the 18 is also 1 by Fermat's little theorem. So that means these are the only powers of 2 that we really need to calculate. And we'll do this by repeatedly reducing mod 19 as needed. So let's notice that 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8, 2 to the 4 is 16. But let's notice that 16 is equal to minus 3. So I'll put that down there just to keep that in mind. Then 2 to the 5 will be 2 times negative 3, that'll be negative 6. So I'll put the negative 6 down here. But in this spot, we really want to write the positive residue. But we add 19 to negative 6 and we get positive 13. So that's the one that we'll keep officially. All right, so next we'll multiply 13 by 2. That gives us 26. Notice that 26 is 7 mod 19. Multiply that by 2 and we'll get 14. Multiply that by 2 and we'll get 28. But notice 28 is 9 mod 19 because it's 9 more than 19. Okay, then multiply that by 2 and we get 18. Notice 18 is negative 1, which will be helpful for the next couple steps. Multiply that by 2, we'll get negative 2, but negative 2 is 17. Multiply that, we'll get negative 4, but negative 4 is 15. Multiply that by 2, we'll get negative 8, but negative 8 is 11. Now we can multiply 11 by 2, we'll get 22, which is 3. That by 2, we'll get 6. That by 2, we'll get 12. Multiply 12 by 2, we will get 24, which is 5. Multiply 5 by 2, we will get 10. Great. And then notice we can stop here. If we multiply 10 by 2, we get 20, which is 1. But we already knew that by Fermat's little theorem. Okay, so now we can get rid of these, which were just helpful for the calculation, and keep this chart in mind. Okay, well, let's notice that 5 can be found in the following spot on this chart. That's over here. So notice that's going to be pretty important, the fact that 2 to the 16 is equal to 5, because 5 is part of our equation. Then furthermore, we see that 2 to the 10 is equal to 17. That's going to be another important part of our congruence. So let's take that into account. So we've got 5 to the x. Well, that is congruent to 2 to the 16 to the x. Again, I just replaced with 5 with 2 to the 16 from our chart. But that needs to be congruent to 17. But notice 17 is 2 to the 10. This is all occurring mod 19. Now we can simplify this a little bit. That gives us 2 to the 16x is congruent to 2 to the 10 mod 19. If the base is working mod 19, the exponent is working mod phi of 19 or 18. So that means we have 16x is congruent to 10 mod 18, 19 minus 1. But now notice that each of these is divisible by 2, so we can just divide out 2. That gives us 8x is congruent to 5 mod 9. But now we're in a good position because 8 and 9 are relatively prime. In fact, 8 is equal to negative 1 mod 9, which means it's its own inverse. That tells us that x is congruent to 40. Again, multiplying both sides by 8. Here we'll get 64, which is 1 more than 63 as expected. Here we'll get 40, but reducing that mod 9, we will get 4 mod 9. So in the end, our answer is x is congruent to 4 mod 9. So we've got x is equal to 4. Then we can just check that. What is 5 to the 4 mod 19? So we can easily do 5 to the 4 is the same thing as 25 times 25 mod 19. But then reduce that. So 25 is the same thing as 6 because it's 6 more than 19. So we have this is 6 squared mod 19. But notice that 6 squared is 36 mod 19. But what's 19 plus 17? It's 36, meaning that 36 is the same thing as 17 mod 19. So that checks our answer. Okay, so now that we've done a couple of examples, let's leave you guys with a couple of warm-up problems. Okay, so I'll leave you guys with 2 warm-up problems. The first is to solve 2x to the 5th is congruent to 1 mod 7. The second one is to solve 7 to the x is congruent to 6 mod 17 using the methods involving primitive roots like we did in the examples from this video. And that's a good place to stop.